This is Why Do I Need to Know Python? I'm a pandas user. We're at PyData London. It is June 18th, 2022. Actually, no, that's not correct. We're actually at PyData New York City. And it is Wednesday, November 9th, 2022. And the reason that I got the date here wrong is because this was actually a talk that I had originally prepared for PyData London. And pro tip, do not change the password on the only laptop that has a copy of your presentation 30 minutes before your presentation is. Pro tip number 2, great password choice is $$, $W0RD. Now, let's see if I can actually give this presentation and it'll be effective. And the presentation here is about, well, you're a pandas user. Why do you need to know anything about Python? Sure, Python, or rather pandas is written in Python, but how much do I really need to know? Tuple versus list? Come on, I'll just try one, and if it doesn't work, I'll try the other. And so to set the tone for you, let's take a look. Let's say that you're a pandas user, and the majority of the work that you do is work like this. You have some time series data, maybe in a multi-index, dates and entities, and there's some signal and some data frame that you're working with. And your data looks something like, let's get this going. Oops, let's actually get this going a little bit better than that. And then we'll get started. There we go. And so you have something that kind of looks like this, and you have some data frame, and the data frame is basically some kind of time series data, entities and signals, and most of the work that you're doing is grouping by this entity, maybe doing a transform. Maybe you saw this lambda as part of some kind of chaining syntax, but for the most part, you just memorize the syntax. What do you really need to know Python for if you're a pandas user? I want to try and answer this question for you by answering this in terms of 4 separate questions. And the very first question that I want to tackle for you is, why do the basics of Python even matter if you're just a pandas user who's doing group by operations, rolling operations, manipulations on columns in a data frame? Well, let's take a look. Let's say you're a pandas user and you're working with Excel data, and you know that there is no guarantee that in that Excel data, the actual table you want to read is in the top left corner. So when you read this in using pandas.readExcel, well, how hard can it be? It turns out you get some garbage like this, because the person who created the Excel file accidentally put the data on the second row, and there's actually 2 data sets in here. You can see there's a first data set and a second data set, and what are you going to do? You're going to go into this data frame and drop the nands and try and extract the data? No. What you're going to do is you're going to use PyExcel. You're going to use PyExcel to actually manipulate this data, to actually pull out what you need, because good luck telling the original author of this data, please fix your data set, it's really screwing up my process. And when you do that, you'll notice, for example, PyExcel does not implement the context manager protocol when you open the file. So you have to learn about contextlib.closing. Because if you write some script and that script is analyzing that file and the script does not close the file, you will find that you cannot rename it, you can't move it into the trash can, you have to reboot your computer just to change the name of the file. So maybe it's worth learning just a little bit about Python, maybe it's worth learning about things like contextlib.closing. But when you take a look at the file, you might say, okay, I want to go into that file and figure out where the data is. And I may actually know where the data is. Maybe it's consistently in some place. So I want to represent the view area for where the data is. And you could represent this as a tuple or a list of lists, but maybe a little bit more readable way to represent this would be as a collections.name tuple, where you can say, this is the minimum and maximum row, minimum and maximum column where I expect my data to be. Maybe it's worth learning about collections.name tuple, because it'll give you a little bit of guidance for how you can extract the data. You can go to OpenPyExcel and say, give me just the cells in this particular location. And if the data set changes, maybe you can toggle these, or maybe you can even write some code that infers where the data is supposed to be by just scanning through the Excel spreadsheet. Whatever the case may be, it might actually be valuable to learn a little bit of Python in order to make this very routine task a bit easier. Now, once you've started down this path, you might say, okay, I've got my name tuple, I've got my OpenPyExcel, I want to work with this data. But what's the guarantee that the data actually has the columns in that order? Because they might not move it around on the spreadsheet, but they might change the order of the columns or even add in extra columns. How do we know that it's name, group, and value? Well, maybe you might be advantageous for you to learn a little bit about Python syntax, maybe what that assert is, because you could add a very simple line saying, assert that the data looks the way that it's supposed to look, and warn me if it doesn't. So if maybe they swap the columns, your analyses don't just break for no good reason. Well, if you're going to do that, you might wonder, should this be an assert or not? And it might be worth learning a little bit about how the Python internals work to understand, for example, that asserts are used for programmatic documentation. They are not for checking business logic. They're for documenting so that somebody knows, as of this line of code, we know that the cells look a certain way. We know that our data has been read incorrectly. And it may require that we understand things like there's a debug variable with 2 underscores before and after that is automatically defined by your Python interpreter that is by default set to true. There's a --O flag that sets that to false. Python's constant folding allows it to elide blocks of code which it knows will never run, and it allows it to elide assert statements. And so those assert statements are not necessarily run if you run Python with a -O flag, which means you could put very expensive data checks behind an if debug flag or in an assert. And when you're running in your debug mode, you can run those checks. But when you deploy this in production, you don't have to run the checks because maybe you're a little bit more convinced that the data set looks right. And in fact, it might be worth learning about things like the disk module so you can see this yourself. Here you can see the assert when I actually look at the code. When I run this with Python -O, it vanishes, which means we now have a way in Python, without learning that much about Python, to add very expensive checks to our code to make sure that our data is correct. And all it took was learning about the debug flag and the assert. Might be worth learning about that. Now, when you are doing your analysis, you might say, okay, I have my data set, I load it in, I defined what the area is, I checked a couple of things, I'm going to create a data frame from it. And it's very likely that that's what you're going to do with this data. You're going to create a data frame, you might use something like toNumeric, and at this point, no big deal. Use all that you know about pandas, read in that data frame, do your group by, everything is fine. Except, what if you have more than one data file? What if you have a bunch of data files and they're in some directory? And it's not just the one data file whose hard-coded path you know, but any of the data files that happen to be in the directory. In this case, this data directory, which happens to have a bunch of data files for the US, for EU, for pricing, for demand information, and so forth and so on. And it even has one data file, this manifest, that maybe I don't want to read in. And it might be worth learning just a little bit about Python, like pathlib.path, because it gives us the ability to very easily manipulate paths on disk. For example, iterating through the paths and finding everything that has a CSV suffix and only processing the CSV files and ignoring any of those metadata files that aren't necessarily relevant for the analytical use case itself. In fact, it might even be worth learning about things like the Python set, because you could put all of the files you want to read into a Python set, and then you could mark any files that you know should not be read, like a bad file that contains corrupted data that, we'll fix that later, but I just don't want to read it for my analysis. You can put that in set and do set subtraction and only process the files that you want. And if somebody says, oh, we fixed that file, no big deal, you could make this an empty set, and everything's good. Or if there's other files you want to skip, you could do that, and you can do it in a very readable way. Now, once you do that, it might be worth learning about things like comprehension syntax, because we can express the finding of all the files that we have on disk and the removal of the bad files in literally 2 lines of code to define these and 1 set subtraction. And here you can see, go to my directory, find every file that's a CSV, ignore this one file for now, and these are the files I'm going to process. And putting that all together, you might then go through the files, read them in, and there we go. We have our analysis with each of the files. Additionally, you can notice that there's an in-band encoding in use here. The file names themselves include information about what they contain. It's in the name, eu.pricing. Maybe it's worth learning a little bit about the string operation so you can do something with that string, like split it into 2 different strings, one of which tells you this is the region that the file contains data for, and this is the region, or this is the metric that it has. And in fact, you might say it might be a little bit worth my time to learn about things like regular expressions, because I can do that just a little bit safer. I can write a simple regular expression that says every file name that I want to process ends with the region and the column that I'm going to create with the CSV file. And thus, I can go through all of my files and only match the files that have this pattern to read them in. I can, of course, remove any bad files that I know are problematic. And with just a little bit of Python, I can do things that would otherwise be extraordinarily manual and extraordinarily difficult. Well, once you start doing that, you might say, okay, I want to read in these files and I want to do something with them. Well, I know that the data types that I'm given by pandas and by NumPy do not nicely grow in place. They are generally dynamically shaped but fixed size, which means if I have to read in a bunch of data, I should probably first read it into a list and at the very tail end do a concatenation. And so here, it might be worth doing something like reading in the data files into some kind of Python dictionary using this dictionary comprehension syntax, doing some kind of concatenation on all the files based off of what the regions are in order to create my final product, which is all of the different data files that I have. Here are the actual data file names and all of the data frames that were created from these data files. I was able to do this in only a couple of lines of code. It might just be worth your time to learn a little bit of Python, even if you happen to be a pandas user. Let's take a look at our next question. And this next question is, why does looping even matter in my life? I'm a pandas user. What do I need to know about looping? Because after all, I learned everything I need to know about looping when I learned about NumPy. I learned about broadcasted and vectorized operations. I learned that when you take two NumPy and D arrays, there are rules that dictate how those are interrelated, how those things may support a particular operation. For example, here you can see I'm doing an element-wise multiplication of these two structures, and it's going to broadcast one to the other. And you might even have taken the time to learn that the broadcasting works by first right-aligning the coordinates or right-aligning the sizes of these, and then matching them up either exactly or looking for a 1. And so here, this is going to repeat this structure 3 times on that axis there. And you say, that's all I need to know about looping. In fact, I'm not even supposed to loop if I'm using pandas or NumPy. Let the restricted computation domain handle that. I want to do everything in those vectorized operations myself. You probably, along the way, have said the word vectorized 16 times already. But why do we need to know about looping? Where does this come up, even if we're a pandas user? Well, it turns out that maybe we have some pandas series. And in that pandas series, we want to do operations like resample this data. And it may not be the case that we want to resample this in some consistent fashion. Maybe one user wants to resample it in one way, another user wants to resample it in another way. Maybe for our analysis, we want to do some kind of rolling, and one person wants to smooth the data by 7 days, somebody else wants to smooth the data by 3 days. There could be a lot of hidden modalities here. But largely, you can see much of the looping is handled by pandas itself, as long as the looping we're talking about is the computational looping. Here we can see some examples of manipulating this pandas series and performing operations like looking up something after resampling this structure on the periods and then finding the mean. And we can even see a little bit of piping syntax here, but it's still not clear to me. He said the looping that I do computationally would be done in pandas. What else is there other than computational looping? Well, it turns out that when we're using something like a pandas data frame, a pandas series, or a NumPy and D array, we are acknowledging that Python has 2 separate domains. The domain where you do your computations, you do these via these kind of operations, these broadcasted operations. And the domain where you describe the problem you're trying to solve, what I like to call program structuring. That's where Python lives, and that's where knowing a little bit more about Python looping might help you, even if you're a pandas user. Because it turns out that when you have your data frame, you might want to do some analysis on it. You might want to do some scenario analysis. For example, you have some low-risk situation and some high-risk situation. And these correspond to multipliers on the columns that you have. In the low-risk situation, you're going to multiply the A column and the B column by these values. In the high-risk situation, you do this. Maybe this is some kind of perturbative risk analysis. Well, whatever the case may be, you definitely know everything there is to know about index alignment. But you might not realize that we can express the scenario analysis very nicely just using simple mechanisms of Python. For example, here I am defining the scenarios that I'm going to apply. I'm going to apply them to my data set. And I have a nice, simple little comprehension syntax that says, for each one of my scenarios, apply them to my data set using the index alignment and give me the results. And you can see this is my low risk and my high risk analysis. How would you do this without that looping syntax? You'd have a bunch of cut and paste code. But, you know, I'm a pandas user. Why do I care? Well, it turns out that the scenario analysis tends to be a lot more complicated than just that. It may be the case that I want to dictate my scenarios, print out the results, but the scenarios aren't just this one, this one, this one in a row. There may be some complex interrelationship between them. For example, I have multiple different scenarios that I want to compare against each other. I have regimes and adjustments. I'm in a low risk or a high risk regime. I'm doing a low overhead or a high overhead adjustment, and I want to look at the Cartesian product. Low risk, low overhead, low risk, high overhead, high risk, low overhead, high risk, high overhead. And in this case, do I really want to be cutting and pasting 2 times 2 4 times? No, because I could use itertools.product in order to set up the structure of the analysis I'm trying to do and compute all of these different scenarios at once in one simple Python loop. It might just be worth your time to learn about the itertools module because it allows you to express how you want to structure your analysis in terms of what are you going to actually be analyzing, even though the underlying computational work will still be handled by NumPy or by pandas. Well, it turns out that this may be an even more effective approach than you think, because this allows you to separately specify what the analysis is going to look like. You can see independently, these are the 4 scenarios I'm going to do, and if I put this into a Python set, I could even subtract out scenarios that nobody cares about. Maybe they want to see the Cartesian product just minus this one case that we don't think is actually going to happen. And I can express all of these in a fluent fashion by just learning a tiny bit about Python. In fact, when I do this, I may discover that I have a very complex set of these scenarios that I want to analyze, and I want to be able to fluently express, don't just do this one scenario, do all of these scenarios, and make it possible for me to just randomly add extra scenarios. I'll make my business users happy if they say, oh, and this one more thing, and it's just one line of code that makes use of all of these looping mechanisms that are provided by the standard library, by the itertools module. But it goes a little bit further than that, because it may be the case that for my scenario analysis, and here you can see the result of my previous computation, for my scenario analysis, I may want to do something even more complicated. For example, I may have some scenarios, and for those scenarios, I may even have, let's go past this one. I might even have some scenarios, and those scenarios are ordered in some linear fashion, like A happens, and then B happens, and C happens, and D happens, and E happens. And I want to compare from A to B what happened, from B to C what happened, from C to D what happened, from D to E what happened. And I could do that using the itertools module. Recently, in the Python standard library, in the itertools module, we added pairwise, which gives us the ability to look at pairs of elements. Here you can see I could do an analysis of my data. Let's get this one going. Where I can compare A against B, B against C, C against D, D against E, preserving that linear ordering, looking at those in overlapping pairs. Very similar to a pandas rolling with a size of 2. Now, I know in the audience we have some people who are looking at this slide and saying, pairwise, what on earth is going on? For those of you, here's NWise. NWise is my generalization of pairwise, looking at windows of any arbitrary size by building from the building blocks in the itertools module, something even more powerful than what it gives me itself. And so here you can see my favorite little iteration helper, NWise. With the idea of NWise, I can do the exact same thing that pairwise has, but if I wanted to look at scenarios with some other window size, like for example, the previous scenario, the current scenario, and the next scenario, I could do that as well. And here we can see just a little bit of looping and a little bit of pure Python gets me very, very far. Here I'm comparing A against B against C, B against C against D, C against D against E, and so forth and so on. And in fact, if I just take that one little idea and take it further, I might write other iteration helpers. I might write iteration helpers like NWise longest or first and last, which then allow me to fluently express exactly what I want to do in my analysis. In this analysis, I want to look at the first scenario all by itself. Then I want to look at what happens between the first and the second scenario, the second and the third and the fourth, and then I want to look at the last scenario all by itself in isolation. And it's just the combination of these tools from the itertools module that allows me to set up a very fluent loop here, which says, look through the previous and the current scenario, identify which is the very first in the order and which is the very last in the order. If you're in the first one, do something here. Maybe as part of your analysis, you may or may not use some sort of factor, or you may perform the analysis slightly differently. For everything else, do this. And if you're at the last scenario, do this here. It might just be worth your time to learn a little bit more about looping, learn about things like the itertools module, even if you happen to be a pandas user. Well, if we're going to talk about looping, we better talk about things like generators. Because you saw in the previous example a generator expression. That's the thing with the squigglies that are kind of like that, the round thing around the thing that has the for in the internet. You're a pandas user, who cares? But when we talk about things like generators, you might say, well, that's good if I have iterators or iterables, but I don't have iterators or iterables. It's a very kind of mechanical thing. Who cares about generators? I'm a pandas user. Well, it turns out that generators are probably the most useful feature in all of Python, semicolon, that you also aren't using today. Because generators aren't just some mechanical thing that makes the Python programmers very happy to talk about iterables and iterators. Generators are your mechanism by which you can express non-closed form operations without specifying the end modality. And that sounds like a lot of verbiage, but I'll tell you what that means. Let's say we have some analysis, and that analysis is done in NumPy. Well, we know that performing operations inside NumPy is definitely a better idea than performing those operations in some loop in the pure Python level. In fact, simple performance analysis shows us that that's the case. Here we have a dot product implemented in pure Python and a dot product implemented in NumPy, and we can see that there is an order of magnitude difference between the two of them. And so when I tell you about things like generators, you might say, well, hold on a second. It sounds a lot like you want me to loop at the pure Python level, which is going to be a terrible performance hit. But it turns out that when we're talking about generators, we're generally talking about a particular regime, a regime that you may not even recognize in your code until I show it to you. Here's how it works. In computation, or at least in Python, we have two ways to represent a computation. A computation, perhaps, that doesn't have a closed form, that can't be done in a single shot. We have eager representations of computation. That's what a function is. It does a bunch of work before you ask. It completes the entire computation and gives you the results. If it's the case that you have some computation that you can break into parts, and the incremental part of that computation is way faster than waiting to ask somebody, should I keep going? Then you do not want to use generators. You want to use NumPy, you want to use pandas, because NumPy and pandas are fundamentally eager computational tools. What might this look like? Well, in the previous example, you can see the incremental computation was a multiply. How fast is a multiply? Very, very fast. To ask the multiply, do I keep going or not, will require going into the Python level, which will take on the order of microseconds. I can do a multiply in much, much less time than a microsecond. And so, when we look at examples where we are doing operations on computational data, it is often the case that we see some perplexing results like what we can see here. Here, I have a NumPy ND array containing values drawn from a normal distribution. And in that NumPy ND array, I am timing the amount of time it takes to find all of the positive values and square them. And I'm doing that with two syntaxes. In the latter syntax, I'm indexing into that structure and squaring all the values that are greater than 0. In the former syntax, I'm squaring every value and then multiplying times a mask. That is only 1 if the value is greater than 0 and is 0 otherwise. This line of code does more work than the second line of code, and yet it's faster. It's over 2 times faster. If it's the case that the incremental computation is so blazingly fast, then it's oftentimes worth it to do extra work and just throw it away, because the time to ask or the time to mask is going to be bigger than the time to do a bunch of computations that you throw away. This is the regime that you're used to, but it is not the only regime in which our computations sit. Because in the other regime, we're talking about lazy computations. And lazy computations are any computation where the time to do an incremental step is significantly slower than the time to make a decision. So if it takes 1 second to compute, and it takes me 1 microsecond to ask, do you want me to keep going? I better ask each time, because otherwise I could waste a lot of computational resources. In fact, anytime I have a simulation, a solver, an optimizer, and in that optimizer I have some ending modality. Simulate for how many steps? Simulate until what condition is met. If the underlying simulation step itself is slow, and by that I mean more than maybe a microsecond of time, it is probably the case that you want to write this as a generator. Let me show you an example. Here I have a simulate, and it runs forever, and it operates on some fairly slow step, performed on some data frame. Now, when I think about how I write this, when I think about how I formulate this computation, I might say, well, my users want to be able to simulate for 100 steps, 200 steps, 300 steps. I'll add a modality. I'll add a numSteps parameter. And that'll be fine until some user says, well, I can't tell a priori how many steps are the best number of steps to run. For my machine learning training, how many steps do I train for? I can't tell unless I look at the data. So actually, can you give me a threshold parameter? Because I want to run this until I see that threshold parameter, and then I want to stop, because otherwise I might be doing extra work. And some other user comes to you and says, you know what? I don't care about the exact values. I only have a somewhat loose time budget of maybe 1 second to train this for before I have to deploy it. So I don't know the number of steps. I don't know the threshold, but I know the amount of clock time that I want to spend in the simulator. And when you want to satisfy all of those users, this is the nonsense that you're going to write for them. 3 different modalities, 3 different parameters to make everybody happy. But you will never be able to make everybody happy, because the moment you show them that you're willing to accommodate such a ridiculous request, they're going to come to you and they're going to say, well, actually, what I want to do is I want to train my machine learning algorithm until the relative improvement between every 2 steps falls under some threshold. Or I want to change that threshold from an absolute threshold to a relative threshold. or I want to support both modes. And you'll see that this grows and grows and grows without bound. Your misery will grow without bound if you believe that any non-closed form operation, which may have different ending modalities, like a simulator, a solver, a machine learning trainer, whatever the case may be, if you're trying to accommodate all of those. But if you use a generator, what you're doing is you're representing that computation as an unbounded sequence of steps, and you're externalizing the control of that computation. You are not preferring any modality over any other modality. You're just running this forever. And externally from the way in which this computation is modeled, your users decide, well, actually I want to run for n steps. Oh, actually I want to run until some threshold is met. Well, actually I want to run for some total time. And in fact, you can write simpler code that has less of a maintenance burden for you and is more flexible for your end users. You can satisfy all of these modalities by externalizing the condition under which the simulation stops. Well, that's all a generator is. A generator is the idea that a computation has multiple steps, but I won't tell you ahead of time how many steps I want to run. I will just structure this computation, and I'll let you externally decide via the itertools module. Well, that's come up twice already, hasn't it? But it turns out that this is a mistake that you see throughout libraries that are computational in nature. And you might say, well, no, people couldn't be missing out on such a big win. scipy.optimize.Newton. Newton's method runs for a number of steps to find the zeros of a polynomial. Let's look at the help text for it. Well, scipy.optimize.Newton takes a max number of iterations, or a relative tolerance, or an absolute tolerance. Those all look like modalities that are trying to decide when do you stop optimizing. And you might say, well, hold on a second, it's scipy. That just means it's probably written in C. Nope. scipy.optimize.Newton is just a big old Python for loop. They should have written this as a generator, because if they had written it as a generator, they wouldn't need those arguments at all. They would have just run the optimizer forever, and then had somebody externally decide, I slice it down to the steps that I want to run. Because all the generator is doing is exposing the computational steps to the interpreter to allow you to decide whether they keep going or not. And this works if it's the case that the incremental computation is slower than the time that it takes to make a decision, which is likely to be the case for an optimizer. Maybe, maybe not, but you're already in the Python level, so you're already paying the cost for it anyway. Now, from all of this, you might see it might just be worth my time to learn about things like generators. In fact, tools like generators are a fantastic way to simplify your APIs while making them broadly more powerful. And this is one of my favorite examples that I like to share with people. This is called the genetic algorithms example. Here you can see I am modeling a genetic algorithm where the incremental steps are considered to be slow enough because it's doing a lot of NumPy manipulation, and I'm doing it by modeling the actual genetic algorithm step as an infinite sequence of steps so that somebody externally can say, run this until I hit a target fitness, or run this for a fixed number of steps, or run until the fitness is no longer increasing. And what I like about this example is hidden within this example, in order to handle things like the single point crossover, you may even use tricks like the masking trick, because if the incremental computation is fast enough, it may be worth just doing extra computations and throwing them away. But if the overall computation is slow enough, then you might want to model this as a generator. In fact, anything that you have where you have a multi-step computation and the computational step takes more than maybe about a microsecond, probably you want to model it as a generator to eliminate all of those modalities that make your code a lot harder for users to use and preclude certain ways of stopping that computation. Now, here you can see my work in play. I want to answer the last question for you. And in this last question, I want to answer for you, why does object orientation even matter? Well, I guess pandas data frame is an object. It's got methods on it. And then NumPy ND array is an object, and it sometimes has methods and sometimes doesn't have methods. Like, why did they put mean on the ND array but not median? Why is that like a function that you have to import? Why is it that in pandas you have mean and standard deviation, skew and kurtosis as methods, but in NumPy you have to import, actually in NumPy you have to import it from SciPy? Well, it turns out that object orientation is something that we can get very deep in the weeds about. But fundamentally, the core idea of object orientation is, how do we find better ways to structure the code in our program? And you might look at this and say, why do I care? I'm a pandas user. Because you know what? I'm more than happy to write some pandas code where I'm basically cutting and pasting things. I have 2 data frames I'm going to operate on. And I'm going to do some operation on those data frames, maybe clip them within some particular region from negative 0.25 to 0.25. And I'm going to subset those data frames, and I'm going to do some grouping. And you know what? Yeah, it's a little bit of cut and paste, but come on, what more do I need? In fact, if it's the case that I see somebody's looking at this code and they're like, yeah, I just did that this morning, right? If it's the case that I see all of this duplication in my code, does it really end? Because when we want to subset it in different ways, you can see this is kind of geometric growth of the cutting and pasting. Here, I'm first clipping the data frames, and then I'm subsetting them on the greater than 0 and the lower than 0, and then performing all the different group bys on each one of these sets. And every time I add another aspect to this, I'm just duplicating the amount of cut and paste I have to have. And almost certainly someone here in the audience has a data frame where, or has a Jupyter notebook where there is df1, df2, df3 underscore temp, df4, and it's basically the same code being cut and paste all over the place. And where that really burns you is, what if I decide to change the column that I'm going to do the grouping on? I got to change it in 4 places. And it's very easy when we forget to change that in 4 places. A little bit of data structuring might help. Well, do I really need data structuring? Because I could write these as methods, right? And I could kind of simplify the logic. I could create a single source of truth for how to perform this operation. And then I guess I could do something like take the grouping and write that as a method. And I could just change it in one place. So I don't know. I still don't see the case for object orientation. I feel like this is just a case where I just need functions. And I'm a pandas user, but I'm at least willing to learn functions because those are the things that get my work done. Well, it turns out that simple object orientation is a very effective way for us to simplify the structure of our code to gain real benefits. Because if we take this function idea a little bit further, we'll see that we start growing modalities and it starts getting very clumsy. We start making certain assumptions of how the data frame looks. And we have all these functions floating around that have all sorts of assumptions about how many columns there are, what the columns look like. And I don't know that I'm really gaining anything because here, even though I have a function, I still have these 2 modalities, whether I'm going to do the greater than 0 or the less than 0. I don't know that I'm really gaining anything or I'm reducing that much cut and paste. Well, what I might do is I might make use of the absolute bare minimum of object orientation in Python. I might use a boilerplate elimination tool like a collections.nameTuple or a dataclass.dataclass. I might create some structure that allows me to give it a data frame and to perform operations to store within it the data frame subject to some sort of data cleaning. I may give it some additional options like, hey, given the data frame that you have, give me the subsetted version. I may say, here's another operation, given the data frame, give me the grouped version. And I can represent the overall analyses as some entity in my program where previously this overall analysis was represented in the program, but in the form of multiple disconnected lines that were cut and paste all over the place. I can group things and structure things a little bit better. And when I do that, I might say, you know what? This might have some benefits. Here is a block of code that I wrote a while back. And it was to demonstrate something that I thought was very interesting, which is to say that when you look at where tuples are allocated in a Python process, and we look at where NumPy and DArrays are allocated in a Python process, NumPy and DArrays are always allocated at lower memory addresses than tuples. And I was really curious, why might it be the case? So I went out and I collected some data. And I collected all the locations of all the allocations over a sample program. And I said, okay, I want to compare all the different ways that these things are allocated to try and understand what's going on here. I want to try and find the pattern programmatically. And as I started cutting and pasting my way through all of this code, cutting and pasting the read CSV code, cutting and pasting all of the manipulation code, I said, I need some data structuring because I'm losing my mind cutting and pasting all over the place. And I reached for the most simplistic structuring that I can have, a named tuple with a couple of methods. I wrote a class that allows me to instantiate some analysis from a CSV file by reading in that CSV file. I wrote something that allows me to instantiate this analysis from some raw data frame. And it goes in that data frame and it does some data parsing. It does all of my little operations to extract the columns that I want, to clean up the data, to parse the data, to split this into multi-index columns, which I wish we had time to talk about. That's another talk called, why do I need to learn how to use pandas? I'm a pandas user. But we'll set that off for later. Here, you can see, I even thought, you know what, for this analysis, I want to see where these different entities are located, so I want to be able to compare them. And I said to myself, I want to use a slightly more nuanced approach to object orientation. I want to, for example, have these methods be named methods, not the underscore methods, because, for example, I might not want somebody to mistakenly distinguish this thing or mistakenly be unable to distinguish this thing from an actual pandas data frame. So I want this to really just be an analysis entity, an entity that represents the work that I'm doing, that programmatically structures how I'm performing that analysis, and that allows me to write this code. This is some of my favorite code that I wrote over the last year, because you can read it and understand exactly what it's doing. Load in my data for the tuples. Load in my data for the ND arrays. The tuple allocation covers a large range. Tell me what the addresses of the tuples are. Tell me how many unique addresses there are. Tell me what the mean and the standard deviation of where the tuple locations are so we can see where these are located. We can even graph them. And here, this is the output. OK. Given that, do the same thing for the ND array. Repeat the exact same analysis. And tell me what's the max location where the ND array was allocated, the min location, the mean and the standard deviation, and the unique. And you can see I have that analysis there. I've cut and pasted into this file. Give me the range of addresses comparatively. Give me how far apart they are, the min and the max and the min. You can see this kind of geometric expansion where if I have 2 characteristics and 2 characteristics, then I'm going to have 4 things that can cut and paste. Well, here I just have the 2 lines answering those questions directly. See if I can discover where the discontinuity is between the tuple allocations. Because when you do this, you actually see that tuples under 59 elements are allocated in one place and over 60 elements are allocated in another place. And you can programmatically show that discontinuity by just taking the structure and computing these grouped by the mean, finding where those groups are, looking at the index min of those 2, and then doing a little bit of index-aligned operations here. And we can see that tuples of size 59 are allocated here. Tuples of size 60 are allocated here. You can visually see that programmatically. Then, for tuples of size 60, assert that they are always before the ND array memory, irrespective of allocation order, and assert the other one. For tuples of size 60, assert that maybe they are before, maybe they are after. And you can see the majority of this code is not the cut and paste to do the analysis. The majority of this code is telling the story of what I'm trying to accomplish, which largely you can see here is somewhat mechanical, but I think is still broadly applicable to the kinds of problems you want to solve. Because ultimately, when we have some computational structure, when we have a data frame, we want to be able to do operations on it. We want to be able to do operations like assign new columns. And we want to be able to do that in such a way where if the data changes, that column is updated. And we might try to do this as a function, but that doesn't quite work out for us. We might try doing this as some kind of analysis object, and we get a little bit of a benefit there. We might even be tempted to do this using something like the registered data frame accessors to extend a pandas data frame to have extra methods like .computed, where you can always recompute values dynamically. But let's be realistic. You're a pandas user. You don't care about object orientation. You don't care about generators. You don't care about looping. You don't care about Python basics. But here's something you might care about. This is a little bit of Python, just a couple of little mechanics that allows you to alias columns. So you can give a column 2 names. So you can give it a really pretty name so it shows up nicely on your matplotlib graphs. And give it a really easy name so you can use that dotted access. And maybe, if you happen to be a data scientist, maybe you might be motivated by the convenience of the things that you can do and the capability to do things that you didn't think possible without cutting and pasting code, without writing code that nobody can make heads or tails of later, writing code that somebody can understand and amend, that they can extend and grow. Maybe you might do that. And if that happens to be you, well, I'd encourage you to follow me on Twitter or LinkedIn. My name is James Powell. But in all truth, why do you need to know about Python? You're a pandas user. Thank you so much.
We have a couple of minutes for questions.
Yes, Juan.
So, thank you very much for the presentation. So coming back to the example that you made with scipy.optimize.newton, I really like. Sometimes it's hard to push that complexity to less sophisticated users, and I've felt that firsthand in several positions. How can we bridge that gap effectively, apart from telling our users watch James talk and then learn some Python?
I've learned a really good way to motivate people is to tell them they're wrong and to criticize them in front of others. They never bother you again, apparently, after that. Another potentially successful way to do this is to understand that almost all scientific or analytical users are under extreme stress to deliver analytical results. In today's market environment, they are under even more stress to deliver. And if you cannot present these in terms of what will save them time, you're just another programmer who's chatting in their ear, telling them things like, has anybody ever tried to tell a data scientist, write a unit test? And they say, no, they're not gonna, right? We have programmers in the room who tell their data scientists to write unit tests and documentation. Does anybody here write documentation and that they tell that their data scientists write? No. So the way that I think you do this is, for every part of Python, at maybe about 30 or 40% deep into the language, there is a very clear motivation for why it exists. You can see here we can map out, look, you can take the path you want to take, and if you take that path, there will be these consequences. If you're okay with that, fine. You are a highly paid professional. You know what risk you're willing to take. But there are other opportunities, there are alternatives that you can try. And if you find that you're willing to entertain those opportunities, there is material benefit. There is a lot in the Python language that doesn't really have that much material benefit to analytical users. If you read through the change logs, there's a bunch of stuff that they add in there where you're just like, come on, nobody cares, right? You know, the statistics module, does anybody ever use the statistics module for anything real? No, they use SciPy, they use NumPy, right? The truth of the matter is, if you can tease apart what actually matters in their life, you can present it to them, and you can have to pick and choose. So these are the 4 examples that I chose very particularly because I know in my own analytical work, I have 2 paths. One path is painful. I want to show you that it doesn't have to be that way. Yes, in the back.
With that same example of the Newton method there,
Yeah?
how would you let's say that they're aware of that and but they don't want to cause a breaking change to switch.
You write a convenience layer. You write a convenience layer that stubs out the intermediary. So you write like Newton slash, I'm going to say something and you're going to hate this, but generally for these kind of closed form methods, or sorry, these non-closed form methods that have some kind of ending modality, generally these are exclusive bounded modalities. You either are one or the other or the other. And as some of us know, there exists a decomposition of a bounded modality. In other words, yeah, nobody knows what that means. But anyway, you can take something like that Newton's method and you can write for them Newton underscore num steps, or something maybe slightly nicer named, and that just hard codes the islice operation, or Newton underscore a tall, and you can create that intermediary layer that doesn't require a lot of maintenance, that allows them to just import something and move on with their life without compromising the integrity of the underlying core code. In fact, raise your hand if you are a user of the core layer of a specific tool called matplotlib. Has anybody here ever imported matplotlib without the pyplot? 1 person in the back, 3 people over here, right? You provide them with convenience layers. You provide them with the pyplot layer. They live in the universe they want to live in, but you keep the core layer sane for people who, like our colleagues in the back, actually want to have that flexibility. Does that satisfy? No? Okay.
I think we need to wrap up.
Fantastic. Thank you so much, everyone.